Welcome to the Nobel interview, Professor Jean-Marie Lehn. You are one of a few French Nobel Prize winners, I would say. How did the prize change your life or academic work?
It didn't change my work because, when you are a scientist, you have a given way of looking at things, and the prize doesn't change that so much. It may perhaps maybe you think about maybe it's time to change field. That's possible. On the other hand, it changed life quite a bit. First of all, one has more to speak about science and chemistry, since because of this resonance this Nobel Prize now has in the society, in newspapers, in media, you are supposed to be sort of a interpreter of science in some ways, to speak in more public occasions, which we must do. One may or may not like it, but one must do it because it's a way to talk about your field, to talk about your colleagues, to talk about what's going on in the area. Maybe more generally even to talk about what science is doing in society, and this is the most important, I would say, because I like to talk about what chemistry has been doing and is doing for everybody, which often is underestimated and very much neglected. But more generally, I think just trying to tell people that science is part of culture, not only literature and arts. Science is also part of our culture. It penetrates our life, I would say, in practical terms, even more than any other forms of human culture.
Science in general and chemistry in particular?
Yes, chemistry is so insidious, I would say, that you don't notice it often. We are sitting here, and I think probably most of what we are wearing is chemistry. Most of the way in which we, when we are sick, what we do, we use pharmaceuticals. What is pharmaceuticals? Molecules, chemistry. So we meet chemistry every time, all the time, the day long. It's hidden. You don't see it in most cases. That's one of the problems. Chemistry is not on the forefront, but it's always there. And people should realize that.
So that's what you're doing officially in France? You talk with people with public?
Yes, no, look, I'm in my laboratory, I do research. But I try, when I have an occasion which is worthwhile, to illustrate. I wouldn't say defend. I don't think science would be defended. That's a defensive attitude. It's more to illustrate and just say what's going on. Also, in present society, having more of what I would call a scientific, maybe a rational approach to societal problems would be very good for people.
After the Nobel Prize, did you consider to change fields, or what did you think?
Yeah, you consider it, but on the other hand, I'm of the type where I like to deduce things from one another. So the field has enormously evolved. In fact, what we are doing now has absolutely nothing to do with what I got the Nobel Prize for. But it is, let's say, deduced from it. It sort of came out rationally out of that by expanding it, by going to other areas. So it is not a change in. It's a total change in subject, in the types of things we are doing in the laboratory, but it is not a change in, let's say, in the direction. There's an evolution which, when you look at it, when you look back at it, looks quite logical.
It's supermolecular chemistry. This is your field.
That's it.
You mean that the field has developed so fast and so that
Yeah, what happens is it is an area which is, some people say, a bit diffuse, which is true because it's very wide. It's at the interface with physics on one hand, material science, with biology, medicine on the other hand, and of course at the core is chemistry. So because of this very large, these very wide interests, the field makes possible many developments in many areas so that they may look very, very different. The general idea in this area is the following, is that molecules are single entities, but in the real world, they're never alone. That means molecules are always among other molecules. Yes. And the properties of collectivities of molecules are not the same as single ones. So that's what we're interested in. What happens to let's say, the real world molecules, which are always together with others? They interact, they do things together, and I sometimes call it a molecular sociology. What happens in a society of molecules? Let me give you an example, which I think also for people who will be looking at this interview, maybe telling them what is the essence of it. Water, which you have in this glass, is a very simple molecule. It's 3 atoms, one H bound to an oxygen, hydrogen, oxygen, hydrogen, a triangle. Okay, an isolated water molecule can be studied and so on, but it has no melting point, no freezing, no seeding, no evaporation. And so when you have a glass of water, this can freeze. A single molecule cannot freeze. So obviously, this is concerned with supermolecular chemistry. What does the collection of water molecules do? These are many, 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 many water molecules. They're liquid. A single molecule is a gas. So what are the properties of this? And this is what we are trying to understand. What happens when molecules are together? What are the properties? And this new property of being able to freeze is something which does not exist for the single molecule.
Well, what is the relation between the properties, for example, of this society of molecules and their structure? Can you deduce properties from the structure?
Excellent question. That's exactly the point. You see, there's this big question, which is a philosophical one. Can one reduce everything to atoms and particles? That's
why physicists do. Yeah?
Yes.
In a way.
In a way, yes. I would say, although I am convinced that there's an explanation in everything, I don't believe one should do the reduction. I call it a deduction. In other words, you cannot reduce the melting or the freezing of water to the single molecule, but you can deduce it from the properties of the single molecule, which interacts with other single molecules. In other words, reduce it to I don't think it's correct, because you cannot reduce it to, but you can deduce the property of the collectivity from the properties of the single. So for me, matter is getting more and more complex, starting from atoms, molecules, supramolecular entities, and so on and so on and so on. And at each level, new properties appear, which do not exist at the level below, but can be deduced from the level below. So you cannot reduce to, but deduce from. For instance, we think, okay? You cannot say that thinking can be reduced to atoms, but it can be deduced from atoms. We are thinking with a brain which is made from atoms, molecules, and all that. So obviously, there is a deductive relationship between the atoms which form our brain and eventual thinking. But you cannot reduce the thinking to atoms. Atoms don't think. So this is my view of things, that you can deduce more and more complexity, higher and higher levels of complexity from the ones below, but you cannot reduce it to.
Yeah. There is this physicist, Philip Anderson, also a Nobel Prize winner, who said more is different. Is this
yeah, in some ways, yeah, you can. This is a very condensed way of saying it, yes. For instance, more water molecules is different, but it's still water. So
more water molecules is different from the one.
From the single one, yeah.
Yes,
So you can, but when you know exactly the property of one water, you can deduce the properties of the liquid water from the single molecule, but you have to take into account everything that happens in the collection. So more is different. More water makes liquid water. One single water is not liquid water. So, okay, more is different. I would subscribe to that too.
What kind of molecules do you study? All supramolecules? No.
Yeah, okay, main life is short, yeah. And days have only 24 hours.
Yes.
I guess that's the trouble. We would like to have days of many, many more hours and lives much, much longer, like everybody. But so you have to select things. So we started with trying to understand simple processes. The idea is the following, that, let's say the way I started is a sort of inductive, where you start from something small and you see that it's wider than what you initially thought, and then you go ahead with it.
When did you start it? When was it?
1967, 66, 67. But it started from what you might call an awkward way. It didn't lead to that. I didn't call it supermolecular chemistry at the start, because you don't necessarily realize when a field is very broad, you get the broad ideas only when you see that what you are doing is more general than what you thought it was. So I was in fact interested in neurochemistry, which seems to be nothing to do with it. In fact, I was interested in philosophy first, because I wanted to study first philosophy. But
philosophy of science or philosophy?
Philosophy in general, philosophy of knowledge. That's what I was interested in. I was extremely interested when I was a youngster in why we think, what is in there now. Which of course is a fantastic problem. But you soon realize that I don't think nowadays we'll have an answer to that. So let's be more modest and start with something where progressively we build up this area, at least progressively approach it. And so I thought neurochemistry, neurosystem has something to do with thinking. So why not start that? And then if you are a chemist, you realize the neural system is extremely complicated and you cannot approach it like that. And one simple way of approaching it is to try to see if there is a process in the neural system which is simple and which one might have access to and might study. And this is the following, which I became then interested in. In a nerve membrane, the propagation of the electric influx, the neural influx, occurs by pumping or by exchange across the membrane of the nerves of two types of ions, entities called ions, potassium and sodium. That's exactly how our nerves function. These run along like this.
Electric
Yeah, it's charge. Ionic, but it's electric charge, a positive charge, not a negative one, but it's a positive charge. And so I thought, all right, these nerve membranes must possess molecules which are able to make the difference between a sodium and a potassium. What's the difference? Both of these entities are spheres, small spheres, and have one positive charge. But one is a little bit larger than the other one. The potassium is a little bit larger, 30% larger, than the sodium. How do the molecules make the difference? If they don't make it, you have a short circuit, you are dead. So they must make the difference. And so we try to understand how you can distinguish a given sphere from a little bit larger one. And we build molecules which have cavities, where you can adjust the cavities. We call them cryptans, and you can adjust the cavities so that they are smaller or larger. And indeed it works. When they're smaller, sodium goes in, when it's larger, potassium goes in, and so on. So you can play with this. That was the start. And then you realize that what have you done? You have done something which is the following. You are able to build molecular entities which are able to make the difference between smaller spheres, larger and larger and larger. In other words, so to say, they recognize a given sphere. They say, oh, this is molecular recognition. Molecules recognize each other. And then you say, sure, if you can recognize spheres, you can recognize more complicated objects. And obviously in biology, all the processes which occur in our organism are molecules sitting together and recognizing each other. When we have an antibody against a given sickness, our molecules we produce, they recognize the antigen, they sit on it and do something with it, they hinder it, they inhibit it. When a virus penetrates into our body, it goes into a cell by recognizing molecules on that cell. Or when in our organism, killer cells, which defend our organisms against abnormal cancer cells, when they do their job, they find the cancer cell, recognize that this is a cancer cell and not a normal cell, and then destroy the cancer cell. This is what they're supposed to do. Now, these are very complicated molecules, but so we thought, all right, like often in science, you have to simplify things to understand them better. So the general idea was, let's develop the area of molecular recognition. How do molecules recognize each other, and develop the basic principles of that, which then, of course, operate in all complicated molecules of biology also, but starting small. So that's where it started, studying molecular recognition. And then, if I may add one thing, once you realize that molecular recognition is something you want to study, which is a very, very widely important subject in biology and everywhere when molecules get together, then you ask yourself, what's the basis of molecular recognition? The basis of molecular recognition is interaction between molecules. what happens between molecules and not inside the molecules. That's molecular
kind of
chemistry.
exchange of information.
Yes, exchange of information and sitting together, just attaching to one another, like water binds to another water. And then you realize that there is a chemistry one should develop, which is not the chemistry of molecules. And for the general public, let me say, the chemistry of molecules deals with the way in which you construct molecules. Molecules are like houses made from bricks, which are the atoms. So you connect the atoms and you build nice houses, molecules. But in a village, you have many houses. And people interact with each other, these houses. They make a village.
This is the sociology.
And that is this area. Then you get into supermolecular chemistry when you consider not just the single houses, the single molecules, but the general organization of all those when they interact with one another and so on. Sometimes I also say atoms are the letters, molecules are the words, and supramolecular entities are the sentences and the chapters, and of course, science is the book.
Oh, this is really a fascinating subject. My last question, when you talk about communication, language is kind of communication, you also talk about storing information in supramolecules.
Yes, this is one of my dada, as one says in French. Huh?
Which means?
Which means sort of, what I like to sort of to express, and I'm especially attached to this aspect, not so much because it needs it, but because in the present society, information is such a big word. And what I usually start with and conclude with in many of my lectures, especially for more general public or for young students, for undergraduates and so on, is that chemistry, of course, deals with matter. Definition of chemistry can be given. It's a science of
molecules are matter.
And of its transformation. What is matter? How to transform matter. Important. Chemists also know how to take one thing and make something else out of it. That's one thing. Matter and energy, obviously, because it's energy. But it also deals with information. And you immediately realize that. I told you a moment ago, molecules recognize each other. How can I recognize you I met you yesterday, okay? This morning I recognized you because I had information about you, all right? How do molecules recognize another molecule? Because they have information. So there must be information, even if it is not, let's say, it's not expressed, or let's say you cannot catalog it or quantitate it the way you, in information theory, define information. Nevertheless, molecules have information and it is stored in the structure. That's molecular. But then the way they interact, the way they get together, this is the reading of this information, and that is supramolecular. So I consider chemical systems, and in fact we are now, that's one of our major interests now, is to study programming of molecular systems. Meaning, you make molecules, you store given information by the structure, where you conceive the structure, then you let them interact. This is reading the information, and by this interaction, there's something coming out of it, which is the output, which is a given architecture, which given some functions.
Yes.
This is the, and so of course, you're saying, obviously, the basic question, since I told you that I was interested in philosophy, if you think about all these problems and make it even more general, then you realize one thing, which is, you realize, it's quite evident, but on one hand, it makes you think. When you start with the Big Bang, when the universe started, it started many years ago. And
15 billion.
At present, what we think is the highest evolution of the universe is the human being. Of course, it doesn't end here. There are things which come afterwards. That's something which is also an interesting question. But in the meantime, starting with the beginning, where there was only energy, then it cooled down, then it make particles, then it make atoms, then molecules. How come the complexification of matter has led to life and to a thinking organism? So, as chemists, we are dealing with what starts when it's cold enough in the universe to make atoms and molecules. And then life started later. But from there on, from the moment it was cold enough to make atoms and molecules, chemistry starts. So I think it's a fantastic problem to try to understand why, what made matter become complex. I have one idea, which is of course so broad that you cannot, just more philosophical idea, but it's as scientific also. I think in some ways one could say it's under the pressure of information, because the pressure of matter has become more and more complex, more and more
instructed. They had to do it, yeah. You mean?
In some ways, yeah, that's such a problem. I don't like this thing where it looks like a dogma, it had to do it. But in some ways, at least, without saying that it is the explanation, there's a parallelism between the age of the universe, the evolution of the universe, and the increase in complexity in some entities in that universe, one of them being the human being. On other planets, there may be even more complicated organisms than we are, or whatever, something more complicated. We know the human being, we cannot go beyond that, at least not for the moment. Maybe someday we'll be able to go beyond it. And so I think very, very, very small, tiny part of that, we hope to contribute to understanding how the universe has led to this very, very complex state and preparing the next complex state.
Yeah, I really hope we'll get the answer
yes,
to the next
unfortunately,
interview.
My impression is we not get it so quickly. We'd like to be around when we get it.
And the time is short. Thank you very much for taking your time. Thank you.
Very kind. And thanks to Mr. Nobel, because it brings people together also.
Yes.